And here then is lecture 10. We're going to go again in chapter 4, and we'll read the last three machines or machine elements that we're going to describe. Heat exchangers, mixing chambers, feed water heaters. Actually, these two are pretty much the same equations, and then throttles. After which we will go briefly into transient behavior. All right, so let's start with heat exchangers. Heat exchangers are devices that transfer energy in the form of heat between two fluids at different temperature by transferring heat between them. So typically, the mechanization for these systems are where one fluid starts in here, goes that way, and the other fluid starts in here and goes at counterflow to the first fluid. These are counterflow heat exchangers. The two fluids, one can come in here and come out that way. The second one can come in here and come that way. These are parallel heat exchangers. And the third is ones where the one fluid comes in this way and the other fluid goes in that way. These are counterflow heat exchangers, some of which you're very familiar with, like automotive radiators. Typically, radiators for them come in two types of mechanizations. You have always the air that comes in the front end of the car, and then you can have the cooling fins going this way and the coolants going between left and right, or you can have the cooling fins going this way and the coolant going between top and bottom. All right, so what are the equations for a heat exchanger? First and foremost, no motion. No motion means no work. That is that. Then each of the fluids, M2 and M1, see their mass conserved. M2 is one value. It's, of course, the density, the velocity, and the cross-section of the first pipe. M2 is the density, the cross-section here, and the velocity of the second pipe. Each are conserved, but of course nobody says that M2 must equal M1, at least not in the type of heat exchangers we describe here. All right, so then we go back to our equation for the energy, conservation of energy, and we will see that we have no work, as I just said. Heat is, of course, what this whole thing is about, and then we are going to see that there is no change in fluid velocities between the first fluid or in fluid velocity in the second fluid. So we are not going to have any change in kinetic energies. The same, we're going to neglect changes in potential energies. And that does mean that the heat that's lost out of the control volume. Now bear in mind that the control volume is the thing where we have the two fluids. The heat out of the control volume, and then the heat that comes into one fluid in the form of enthalpy, and the heat that comes in the other fluids also in the form of enthalpy has to be conserved. Now let's put this whole thing together. Assume further that we have no change in heat in the control volume. In other words, we neglect heat losses at the place where the heat exchange happens, and we say that the only heat exchange happens between the first fluid and the second fluid. Then you plug through the equations here, and you see that the mass flow rate of the first fluid multiplied by the change of its enthalpy has to be equal to the mass flow rate of the second fluid multiplied by the change of its enthalpy. Of course, the signs of these enthalpies and entrances and exits are important, and the signs are given in the equation that I have here. So that 0 equals this plus that. That is really the equation that we will use for all heat exchangers. Mixing chambers are a particular kind of heat exchanger in reality, but in which you have the two fluids that come in contact. So in this case, we'll have a fluid 1 that flows in, a fluid 2 that also flows in, and a fluid 3 that flows out in this particular example. Here you have mass and enthalpy, mass and enthalpy, mass and enthalpy, and we will see that the equations that matter here is the conservation of mass and the conservation of enthalpy. In other words, the fluids in 1 and 2 can come in at two different states in the thermodynamic tables. They can come in at two different temperatures, different pressures? Well, not necessarily. Here the pressures will have to equilibrate. But at the end of the day, they will have to equilibrate both energy and mass. I have a rather funny example here of a mixing chamber. It's this thing. You wonder what that is, this machine here. It's a fancy form of a still. It distills alcohol. And so we have the boiler here, and the alcohol comes here, and the vapors that come from the distillate are used to preheat the thing to be distilled in essentially a mixing chamber here. All right. Another class of materials, of devices, is throttling devices. So throttling devices aim at reducing the pressure. Now, the mechanization can be quite complicated, but we have to define our thing as this. We have a tube in which we have a narrow orifice in some way or some other. And I'll explain in a minute how we get this narrow orifice. Now, we have to define the control volume in this particular throttling device in such a way that the cross-sectional area at the entrance and the cross-sectional area at the exit are the same, so that the velocities are really going to be the same, since the mass in has to equal the mass out, but not the pressure and not the enthalpy. All right, first again, you see that in this device is nothing that moves, so there is no work. Let's assume further that we have no heat losses in the throttling device itself, no heat, and we write our equation of conservation of energy. Conservation of mass is obvious, and what goes in comes out. Well, for energy, we have no heat, we have no work, and we will neglect changes in kinetic energy, and we will neglect changes in potential energy. And so that really means that 0 is 0, 0, this 0, this 0, H in equals H out. That means that a throttle is an isenthalpic device. It is a device that mechanizes an isenthalpic transformation. Let's take a look at what that would mean in a PV diagram, which by now you're quite familiar. Here is an isotherm, first isotherm. Here is the second isotherm in the PV diagram. And let's say that you set from this point here on the saturated liquid line. If you send that through a throttle, your isenthalpic transformation will get you here. That's what it looks like on a PV diagram. And that's what a throttle does. Now, we have to be careful when we talk about throttles. So clearly, a throttle is designed to lower the pressure and lower at the same enthalpy. But we derive this as an isenthalpic transformation because we derived the control volume in this fashion, so that the cross-section at the entrance and the cross-section at the exit be the same. You could, of course, have defined your control volume here, where the cross-section at the entrance is here, but the cross-section at the exit would be here. So it's exactly the same device, but you change the definition of control volume. Now you actually have a nozzle, because you have a different cross-section than here and then here, and you have a reduction in pressure, but that comes at the expense or the increase of the velocity at the exit. So then, while here you're right, between here and here you have an isenthalpic transformation, between here and here you're transforming your enthalpy change to a kinetic energy change. So careful how you define your control volumes. For the throttle, we call it this. For the nozzle, we call it that. But ultimately, of course, these devices work the same way. So you would have a throttle to be a nozzle plus a diffuser. That would give you a throttle. Why do we use throttles? Well, an arch example of where we use throttles, and you will see this in chapter 10, is in refrigeration cycles. In a refrigeration cycle, we're going to take a saturated vapor or even a superheated vapor here. We're going to compress it, bring it up here. We're going to send it through one heat exchanger, which will get it here. And then here we send it through one of these throttles, which is there called an expansion valve, but it is the same thing. So here we get this isenthalpic transformation. You don't need to learn this cycle yet. We will see this cycle in chapter 10, but I wanted to make it clear that these devices have their use. You're quite familiar with another use of a throttle, and that is just your faucet. So a throttle would be a pipe, and another pipe here, and a little plunger that comes and reduces the orifice, the dimension of the cross-sectional area of the pipe at this location. Of course, you can close it completely. That's no longer really a throttle. But if you open it partially, you'll have much less pressure here than there. And that's a good thing, too, because in your faucet, the pressure of the water typically is on the order of 7 bar, which is actually quite a lot of pressure, whereas water that you use at a much more reasonable pressure and flow rates. The flow rate is determined by the pressure and cross-section at the exit. Actually, it's determined, Bernoulli's equation applies to the flow rate. It's determined by both this orifice and the velocity of that, which are related to each other. You'll see that in fluid dynamics, or you could derive it from the equations that I have given you here. Another typical throttle is to just put a porous plug in a pipe, and then the gas or the liquid has to go through the pores of the porous plug. An alternative to the porous plug, which would be the simplest thing you could do, would be simply to put a crimp in the pipe. Here, you don't even need the pores. You take your pipe, you put a crimp in it, and that is going to be a throttle. Now, let's move on to something a little more complicated here, which is the transient analysis. So when mass or energy change over time, you cannot write these steady-state equations. And then you have your mass flow rate, which we developed into a mass flow rate inlet and outlet, now becomes integrated from 0 to time t dt, 0 to time t dt, 0 to time t dt, which eventually gives you even differential equations when the variable that shows up here also shows up here, as we have seen in one of the exercises. Well, that means that the change over time of the mass, so the mass at times t minus the mass at times 0 in the control volume, is going to be the integral over time of the flow rate in minus the flow rate out. And then eventually this would be given by such an equation. Because the integral of the flow rate is the total mass here as well as there. So this is the mass and this is the mass as well. In other words, if you have a vessel and you let a faucet run for a little amount of time, and you have a plug in there, so there's no exit, the amount of water in your container is going to be the amount of water you have put in through the faucet. That's what this equation just says. Now, the same equation, as usual, when applied to energy, becomes far more complicated. But it's exactly the same idea that we have to apply. So let's first neglect kinetic and potential energy. We write back our total equation about the total energies as an equation about the internal energies. So internal energy at time t minus internal energy at time t0 is total heat, total work, and then the integrated value of the enthalpy over time at the entrances and at the exits, at the inlets and at the outlets. Now, this can be rearranged. So consider that the state at the inlet and outlet do not change with time. So let's take a minute the assumption that m dot h, well, first let's assume that h does not vary over time, so we can take it out of the integral. So then we have h sub I times the integral of m dot dt, which we saw last time is simply the amount of mass that goes in. So you see that the word that goes into the system is the enthalpy of the system, of the state of the fluid, times the mass that you have put in your system, same at the exits. And so you can rewrite this equation as change in internal energy is heat, work, and then sum of enthalpies of mass in and enthalpies of the mass that goes out. Be careful, this was different from what we had in open systems that were in steady state. In steady state, this is 0, and we only had to consider the enthalpies. In transient states, This is not zero, but these are internal energies, whereas these are enthalpies. So transient states is a place we can mix internal energy and enthalpy within the same equation. Whereas in open systems, steady state, you always had this to zero and you didn't worry about anything but enthalpies. Masses, of course, in the control volume are specific volume, volume divided by specific volume, and internal energies are masses times specific internal energies per volume, per specific per mass here. Let me just go over all the equations that we used in chapter 4. So, in steady state systems, you use reflexively internal energy for closed systems, enthalpy for open systems. In steady state where you have only one inlet and one outlet, you need to worry only about one value of the mass. And then your equation becomes this general equation that we have used quite a few times. So equilibrium and steady state comes from the balancing the rate of heat exchange in the control volume, the rate of work in the control volume, and the mass flow rate multiplied by changes in enthalpy, changes in kinetic energy, and changes in potential energy. Not so if you don't have steady state. In systems with transients, you of course can integrate the mass, that's relatively easy, but then you have the integral of the internal volume is a function of heat, work, and the additional energy that is brought in as enthalpy. Now you're mixing internal energy and enthalpy in the same equation. And then we went through a number of mechanizations for nozzles, which increase velocity, or diffusers, which decrease velocity. What you're really doing, if you neglect the heat losses, so if you set that to zero, is you're exchanging changes in enthalpy for changes in kinetic energy. Nozzles, you increase the kinetic energy. Diffusers, you decrease the kinetic energy. That's a question of the shape of the device. In turbines, what you're doing is the fluid does work on the mechanization, whereas in compressors and pumps, the mechanization does work on the fluid. But the equations are the same, and they tell you essentially that work is going to be due to changes in enthalpy given a mass flow rate, eventually with changes in kinetic energy. Compressors and pumps, pretty much the same. If you neglect the heat losses or the heat changes of heat in the turbine, you are going to exchange work for changes in enthalpy. Heat exchangers, on the other hand, are things where you change the temperature of one fluid from the other by transferring heat between a hot side and a cold side. So mass and enthalpy that go in come out. You conserve your mass, mass in equals mass out on all sides of the heat exchanger, and your exchange of energy means that the enthalpy change that comes from the first mass flow rate must correspond to the enthalpy change that comes from the second mass flow rate. And finally, we have throttles and valves that aim to reduce the pressure, but anytime you have a throttle, you conserve enthalpy, and of course you conserve mass. What you change is pressures, flow rates, things like that. Thank you.